Okay, so I mentioned the use of certificates for large tree width in the overall proof of the graph-minor theorem, the quasi-orderedness of the finite graphs under the minor relation, when we introduced brambles as particular certificates of large tree width, large order brambles. And just as a reminder, it's easier to prove that graphs are well quasi-ordered when they have bounded tree width, a lot easier. So the idea is that if you have your infinite sequence of finite graphs and you want to find a good pair in the proof of the well quasi-orderedness, then it helps to assume that all these graphs have tree width at most some k. And that's not always the case. And if it's not the case, then you want to buy something for it. You want to say, oh, well, then there is this or that certificate that must always occur when tree width is large. So there must exist some kind of large, dense, whatever substructure in G that certifies that the tree width cannot be small, cannot be bounded. And then you know that these substructures exist in your graphs that don't have bounded tree width. And then you can maybe use these substructures to find a good pair after all. That's the overall view on why we're looking for certificates for large tree width. And we had one, that was brambles of large order. And here's another. Large, highly connected sets of vertices. And highly connected is intended to be outside, or possibly outside, the set itself. So the connectivity can reside elsewhere outside that set. So a set X of at least k vertices is going to be k connected in G, going to be called k connected in G, if for all subsets Y and Z also of size at most, these have size at most k, X has size at least k. For all such sets, and we want them to be equally large, there exists somewhere in G disjoint paths linking them up, as many as you have vertices in these two sets. So these, when the sets intersect, then these paths are allowed to be trivial, in fact, have to be trivial. Right, so X, size at least k, is k connected in G if for every choice of equally sized subsets of size at most k of X, you can join them up disjointly by paths that can run anywhere in X. Okay, and here's an example. If we have a large grid, then if we take as X the bottom row, then we can find such paths. So the bottom row in a large grid is highly connected in the grid. And here's Y, so if we have our Y and if we have our Z, then we want to find disjoint paths, and that's easy. So we start by taking the intersection as trivial paths, and then we just work from the inside to the outside, just joining them up through the grid. All right, so something like this. Came down too early. something like that. You know, we can, that always works if the grid is square. So that proves that this bottom row here of vertices is k connected for k, the length of the grid signs. Right? For a k by k grid, the bottom row is k connected in that grid. Okay, so you may remember the definition of a k-block. Right, a k-block also appealed to this external connectivity, and a k-block was a maximal set of at least k vertices such that any two can be joined by k independent paths, or as the definition said, cannot be separated by fewer than k vertices in G. And that is a stronger condition, right, because it requires something for every two vertices. So in particular, the vertices in a k-block have to have degree at least k in order for this to be possible. Otherwise, they could be separated from each other by fewer vertices. And here, you don't need any vertices of large degree at all, right? So you can turn this into a k-block. We had this example too by attaching some at least k vertices with a fan like this disjointly, and then those outer vertices will be a k-block using the same connectivity as we have it here, like that. Okay, but just keep the two notions apart. They're both useful, but they're different. Okay, and then I just for this lecture, I gave one particular occurrence of this a special name called star, and that is the existence of a k+1 connected set of size at least 3k. There's nothing magic about it, it's just that it occurs 3 times, and I don't want to write so much, right? And then we have this theorem, which I want to show you first, and that says that large, highly connected sets are qualitatively necessary, always occurring certificates for large tree width. So if the tree width is small, then we can't have star, we can't have a k+1 connected set of size at least 3k. So if the tree width is small, we can't have a large, highly connected set. And if we don't have a large, highly connected set, precisely with these parameters here, then the tree width is small. Not, unfortunately, as small as this. We lose a factor of 4. But the upside of that is that the proof is really easy compared with the tree width duality theorem with the brambles, where we had an if and only if, but the proof was rather harder than what's coming now. Questions about the definition setup or anything? Nope. Okay, let's prove 1 then. We just wipe the board a little bit. Yes. Sorry? Yes, good question. We're in nowhere. We're in the exercises. So feel free to take a photo, either now or when I've found all the mistakes. Right. This used to be preparation for the proof of the grid theorem, which is no longer in the book either. Yeah, so it's additional material. Entirely free. Okay. I wanted to prove 1. If the tree width is small, less than k, we can't have set x of size at least 3k, that is k+1 connected in the graph. So suppose we do, and the tree width is small, so less than k, then what does it look like? We have a tree decomposition. Something like this. And the bags have size at most k. So the tree width is less than k, and I'm taking the witness for that. A tree decomposition of width less than k, so the bags have size up to k. And we'll log these attachment adhesion sets here. I want them to have size less than k. That can always be achieved. That's an easy exercise. All you have to ensure is that the parts don't contain each other. And if they do, you can just delete some of the parts and contract the tree a little bit. So such a tree decomposition exists if the tree width is less than k, one whose parts have size most k and adhesion sets have size less than k. Right, and then in there somewhere is our set X, right? So X is somewhere, and it has size at least 3k. So that means that for any such separator, because it has size less than k, we can't have k vertices of x. Let's look at this separator here, this adhesion set. We can't have at least k vertices of x on this side and at least k vertices of x on that side, because then these vertex sets could be used as y and z, and we should be able to join them up by k independent paths. But we can't, because they have to go through this adhesion set there. So on one of the two sides in any such separation, there are fewer than x vertices, than k vertices, which means that on the other side there must be more. And because we have 3k vertices in x altogether, so we get an arrow in the by now familiar way on every such adhesion set pointing to where more of x lies. All right, so we get all these arrows, and as usual, we can find a sink in this decomposition tree. So here's the sink. And then we do a few more calculations. We're aiming for a contradiction, right? We're assuming that the tree width is small, so we have such a decomposition that witnesses that, yet star holds, we have a k plus 1 connected set X of size at least 3k, so we want a contradiction, and the contradiction will be centered on this sink part, Vt. I mean, this is going to be unique, as you know, but we don't need that. So all I want is that it's a sink, and what I'll be using is that all these arrows at the decomposition tree edges at that node point towards that node. Right, then yeah, I think I'll redo that picture, or maybe just put another picture next to it. So here we have our VT, again, just enlarged a little bit and without so much mess. And now let's look at the other side of these separations, each of them. And I claim that there are at most k minus 1 vertices here. I just proved that earlier. So, and at most k minus 1 here, and at most k minus 1 here. And now we do a funny trick. We collect components like this, or unions of components if this is not connected. Let me call them components. What I mean is the union of these parts on the other side of such an adhesion set taken over the nodes of that, the decomposition tree. That makes a component when we delete this edge, and whether or not that's connected when you delete this edge, I don't care. Let me just call it a component. So for every such component, we collect such components, 1, 2, 3, maybe 27 of them, until, now I have to get this right, they cover more than k vertices of X. So collect C's until more than k vertices of X are covered. Right, we start with one component that has, does not have more than k. And then we keep adding such components, each time adding at most k minus 1 vertices. And since we're always starting at something, we only continue when we have at most, if we have at most k vertices of X in our union of components. So at the last step, we're adding at most k minus 1 vertices to at most k vertices that we have so far. So we have at most 2k minus 1 vertices in this union of components that we have collected. All right, so let's say, no, other color. We have collected this one, a few more here, this one, but there we stopped. So X has 3k vertices at least. We have at most 2k minus 1 here, so there's at least k plus 1 left in VT possibly, and in any other components, at least k plus 1. So k plus 1 vertices of X lie in the bag itself and in any components we haven't collected. Right, but now this is more than the size of VT, right? VT has at most k vertices. There. So choose Z from the vertices we've collected here. That's more than k, so more than enough to make a set of k vertices and call it Z, and choose Y from the rest, and then we have a contradiction because Y is separated from Z by at most k vertices, those in VT, and therefore we can't have these paths. Okay? Questions? It's a nice trick. We will be applying it 3 times, I think, today. Okay. Then let's proceed and prove 2. And for 2, I want a slightly different, stronger notion than k-connectedness in G, and that is external k-connectedness in G. So take the definition of k-connectedness in G as it is here. Oops, as it is where? Yes, up here, right? And now strengthen the requirements in that we're not allowing these paths to contain anything from X other than their first and last vertex. In particular, not the edge. Right, well, X is the size of vertices, so that's an additional requirement. We're not allowing paths of length 1 from Y to Z, from Y to Z. They have to, all the edges they use are outside what X spans. And all the inner vertices are also not in X, right? That's called externally k-connected. That's a stronger notion of being k-connected. And so rather than proving true, we're proving that we're proving dagger. Right? If X has no set of, let's give it a name, that's the size of X called little h for later, of at least k vertices, same as here, that is externally highly connected. Right? So we're assuming more. Then the tree width is at most this, and that translates to this if you replace k by k plus 1, I'm afraid, and h by 3k. Right? So we're proving this statement now, and that implies this statement if you replace k by k plus 1 and h by 3k. So this is neater, this is nicer to read because you see how much you lose when you invert the implication, but this is a more technical statement that's actually more useful, and we'll see how it's useful later today. Questions about this? Okay, then let's prove statement dagger. We're assuming this, and we're going to construct a tree decomposition, and we possibly get stuck, and we'll see that we'll get a contradiction to our assumption if we do get stuck. So what's the recipe for constructing the tree decomposition? Well, we just start. Always observing this. So the bags have size at most h plus k minus 1. And we're observing two properties that are necessary if we even want a chance to succeed. And one is that for every component of what we haven't covered, all the neighbors of that component in what we have covered are inside some suitable bag. So this component is not allowed to send an edge to a vertex that isn't in this bag, if that's our chosen bag. Right? And you can see that since components are connected, we would be off to a really bad start with this partial tree decomposition here. We wouldn't be able to complete it because in the finished tree decomposition, if indeed we were able to finish it, this separator here would separate everything that grows in the tree decomposition here from everything here, which includes that, right? So in the finished tree decomposition, if you just look at how it continues, this separator here separates any component that meets things in here from everything we have covered so far, including from the other parts. So we'd better assume that. So the assumption is for every component C of uncovered portion, to avoid the word part, portion of G, the neighborhood of C is in one part. And has size exactly H, so this neighborhood, right? So let's look at this. Okay. Yeah, why not down there? This is not allowed. This has size exactly H. No, I'm not assuming that. At most H. Most H. We're going to show that exactly H, but we're assuming at most H. All right? At most H. Okay, so we start decomposing and see how far we get, observing these two requirements. Now, I want to show that we can finish the decomposition, there's nothing left. If there's no vertices left, then we have, yeah, that's another thing one ought to check, that one has also covered all the edges. Yeah, so bear it in mind, I'm not going to talk about it now. Suppose there's anything left that we haven't covered, so suppose there's some vertices left, in particular, there's a component C left. Then I claim that the neighborhood of this component here has size exactly H. And why? Well, if it didn't, we could just add one more vertex, one point in that component that sends an edge to this neighborhood. And attach this as a new bag. Right, that would grow our tree decomposition a little further. We would really be adding something, and we'd still be adhering to these two conditions. Why? Any component of the rest sends all its edges to one part. Well, that's true for the components that live outside C. There may be some components that live inside C, maybe more than one if this vertex separates C. But what can they see? All the edges they send to the part we have covered are either in here, because they're in C, or the new vertex. And all this is inside one new part. Okay, so we have been able to extend the decomposition if there are fewer than H vertices here. So we know there are exactly H vertices here. Okay, can I wipe? So this is N of C, the neighborhood. There's exactly 8 H vertices. Right, and now we use wait a minute. What does Dagger say? Oh, yes. Dagger says that we have no set of exactly H vertices that is externally highly connected. Right? That's part of our assumptions. So this set X here, the neighborhood of C, is not externally highly connected. In particular, we can apply this externally just to the component. Oh. There exist sets Y and Z in this neighborhood, equally sized at most K vertices each, and these cannot be externally joined by disjoint paths. Nowhere in G, let alone just through C. And now we apply Menger for, well, C union X, with all the edges from C to X, but not with any internal edges. Okay, that's the graph. Okay, shall I write this more properly? It's cumbersome to write it more properly. There we go. For the graph C, or what NG we can induce by vertices of C union neighborhood of C minus the edges of that live on the neighborhood of C. Right? Everything in C plus the vertices they can see, but no edges on X. Okay, and then Menger gives us a separator. Let's make it red. Separators are horrible things. So the separator is going to include the intersection of y and z, so it's something like this. Separator of size less than k, right? Because x, y, and z have size k. Okay, and now we do something similar to earlier. We extend our tree decomposition by x union S. Right? This is x here. X is the neighborhood of C. Right, let's check whether that satisfies what we want. It's a tree decomposition whose bags, or the new bag, has size at most h plus k minus 1. Because this is h, S has at most k minus 1 vertices, so even if S didn't meet the neighborhood, it would be, the new part will be small enough to be allowed. Then so the requirement here, I forgot to correct that. The requirement here is that the neighborhood has size at most h, right? Here. And then we proved that if the tree decomposition can't be extended, it has size exactly h, but we're going to get a contradiction anyway. So we have to check that for all components of the uncovered portion of G, all the neighbors are in one part. And where are these components? Well, same as before. These components can be somewhere here, so that could be a component, then it sees what it used to see. It could also be a component contained in C, and these components, what can they see? Well, all their neighbors are in this new part here. That's not good enough. Well, that's good enough for this. But we also need that there are not too many neighbors, at most h. So let's look at this component. It has some new neighbors in S, but it also has some neighbors that it can't see anymore, and those are the ones in Z. Or more precisely, those in Z minus S. But here the new ones are only those in S minus Z. And so we're replacing Z in the neighborhood of C with S in the neighborhood of this C prime here. And that is not going to be bigger than before. In fact, it's going to be smaller. Right? And similarly for a C prime that's on this side, that can't see Y, except for vertices that are in S. Right? That's because S separates Y from Z. So no component can see both Y and Z. Okay, so we've got this as well. And there we have our contradiction. Easy. I mean, compared with all we've done before, all this is baby stuff. It's really easy. Oh, one last thought. Have we added anything? Yes, we have added something. So S can't just sit entirely in here. It has to have a new vertex. We take a vertex from Y minus Z and another vertex from Z minus Y, and we can just go into this component. Remember, this is the neighborhood of that component, and then join them up there. So S has to meet that component, and therefore we really did add a vertex. Right, so we have the following qualitative equivalences. We have just proved that there are large, highly connected vertex sets, if and only if the tree width is large. And large can have various meanings. So large sometimes can mean at least k, or at least 4k. But qualitatively, we have both directions. So we have seen this equivalence here, and that is just the tree-width duality theorem, which you know. Right? So if we have large tree width, then this is witnessed by large order bramble, and conversely, if we have a large order bramble, then the tree width cannot be small. Right, so the implication from middle to right was the hard one. Remember, that was the non-trivial or the hard direction of the tree-width duality theorem, where we used the petals and all this, right? So it's tempting to say, well, if we only want a qualitative equivalence, if we don't mind losing a factor of 4, say, then we can now try something clever and prove the implication middle to right in a roundabout way. We can go from the middle to the left and then see if from the left we can deduce the right, and then we have the same thing. Okay? And that's what I'm going to show you now. And that's here. If we have star, there exists a highly connected set X. So star says there is a k plus 1 connected set of size at least 3k. Implies there's a bramble of order at least of order bigger than k. Right, so we're going to prove 3. This 3. Nearly. So that's true, and in fact that comes out if you do the direct concatenation of the two implications. If you go from left to middle to right using the tree-width duality theorem as we proved it, then you get this. So you lose a little bit, but I'm going to show you something slightly weaker. I'm going to show you that if we have a k plus 1 connected set of size at least 3 k plus 1, then we have a bramble of order greater than k. Yeah, so proof of 3 for x bigger than k, 3k. Yeah. At least 3k plus 1. So we have to construct a bramble of order bigger than k. How does one create a bramble of order bigger than something? Well, one has to show that the non-somethings cannot cover it. So we have to find for every set, I think I want to call it S, yeah, for every set S of size too small, in this case at most k, there is a bramble set it doesn't cover. Well, we don't have a bramble yet. We want to create one, but that it will have to have an uncovered set, a set not covered by S, right? So since it's going to have one, we may as well invent one when we construct the bramble. So for every set S of at most k vertices, which is not allowed to be able to cover the bramble, because the bramble should have order bigger than k. We have to invent a bramble set. And that's going to be one of these components of the rest. I claim that we can find a component that contains at least 2/3 of x. So claim there exists a C such that x intersect C union S is at least 2/3 of x. That's my claim, and I want to show you why such a component must exist. We employ the same strategy as earlier. So we collect components together so that the union of the components we have collected together with S contains at least 1/3 of x. Collect C's until S union these C's is at least 1/3 of x. If our first component already satisfies this, then obviously we're done. So we keep adding more, and before we added the last one, we have covered fewer than 1/3 of x, vertices of x. We have covered less than 1/3 of x with the components we have collected so far and S. Then we add the next component. The next component adds less than 1/3 of x, because if it had more, if it had at least 1/3 of x, we could have taken just that component. Right? So we started from less than x/3 of the components we had so far together with S, and now we're adding one more. Then what we have when the collecting terminates is at most 2/3 of x, as I just showed you. In fact, I think less than 2/3. But now we have a contradiction, because now we find a k set in this collection of components plus S, which we can because we have now collected at least 1/3 of x. So that's just a little more than k. K and 1/3 or something. But since vertices are whole things, we have collected at least k+1 vertices. But we also have not collected some other k+1 vertices, right? Because we only we have less than 2/3 of x. So there are some k+1 vertices that we have collected and some others that we haven't collected. So let's say we've collected these components, and then in all these components and S, there are at least k+1 vertices from X. right? Not just in here, but in this entire thing. And so like this. And here are also at least k plus 1 vertices from X. But that's a contradiction because S has size at most k. Right. Okay, so where are we? We have proved this. We've just proved that. And that implies that there are more than k vertices of X in C itself. 2/3 of X. X is bigger than 3k. At most k line S, right? So more than 1/3 of X is in the actual C itself, and that's more than k. Oh, I forgot to say, choose this component that we have found and put it in our bramble. Okay. Right, so let's prove that these components form a bramble. If they do, this bramble will have order bigger than k, because any k set can be taken as S, and then there's a component that misses it. So the order will be right, but we have to show that they touch. So let's just take any bramble set. Here. And let's take some other bramble set, C prime. And we have to show they touch. Right? Either intersect, have a vertex in common, or there's an edge from one to the other. Okay, let's look at the neighborhood of that component. Or more precisely, let's look at the S that gave rise to it. Every C in our collection comes from some S. We want to show that C touches some other arbitrary C prime. And the question is, where can C prime lie? So maybe we have some more components here. C prime is going to be a connected set. Is it possible that C prime lies inside one of the other components of G minus S? No, that is not possible, because C and C prime each have more than k vertices of X. Just inside them. So there are at least k plus 1 vertices of X here, there's at least k plus 1 here, and we could choose those two k plus 1 sets to contradict the k plus 1 connectedness of X. Right, if there are k plus 1 here, k plus 1 there, and there's a separator of size at most k there, then we have a contradiction. So C is not inside one of these components. So so it has to have a vertex in S, and unless, of course, it's, I don't know, unless it's C or something. And therefore, this is a neighbor of C, and therefore C and C prime touch. Question? Okay. I'm doing well in time for once. I got so scared of always overshooting, so I wrote all this up. Now, there's another certificate, and we're going to get to that now for large tree width. So we have the second certificate, that's large, highly connected sets of vertices, or even, if you like, are large, externally highly connected sets of vertices. And the third is going to be large grid minors. So you have to get the bracketing right here. It's large grid minors. Large grids that occur as minors certify large tree width. That's clear because they, large grids have large, highly connected sets, and therefore imply large tree width, or they have the crosses bramble, which has high order, and therefore imply large tree width. So third certificate of large tree width, large grid minors. Right? It's not that the minors are large, it's that the grids that are minors are large. Okay. Grids have arbitrarily large tree width. So if we consider a graph property that has arbitrarily large grids as minors in the graphs of that property, then the tree width of the graphs in that property is going to be unbounded, right? If the tree width of a grid is large, which it is, then any graph that has a grid as a minor can't have tree width lower than that, because tree decompositions are passed to minor. Right? So any graph property whose elements, so a class of graphs, infinite class of finite graphs closed under isomorphism, any graph property whose elements contain arbitrarily large grids as minors has unbounded tree width, meaning for every k you can find a graph with that property of tree width bigger than k. Okay, and the converse is true as well. So for every graph property of unbounded tree width, its elements contain arbitrarily large grids. And that is Grid Theorem. Which says that large tree width implies large grid minors, right? But the large now, the two larges differ not just by a factor of 4, but immensely. All we can say is that if we want to force a large grid minor, it will be enough to make the tree width f of r big. So for every r there exists a k, such that graphs of tree width at least k contain an r by r grid minor. K is going to be huge, depending on r. Right? But the point is, if you look at graph properties and whether the size of grid minors in there is bounded or not, and whether the tree width is bounded or not, then the two are equivalent, because both tend to infinity or neither does. So a corollary if X is a grid, then excluding it as a minor has bounded tree width, forces the tree width to be bounded. So the class of all graphs that don't have X as a minor, don't have this grid as a minor, has bounded tree width. That is the grid theorem, right? If the tree width was arbitrarily large, it would be in some graph large enough to force this particular grid as a minor. So this is forbidden minors, right? Okay. If we forbid not just a grid, but anything that's contained in a grid, say as a minor, so very weak, very general containment, then that still works, right? If we forbid something that's a minor of a grid as a minor, then the tree width is also bounded, because if it wasn't, then we'd contain arbitrarily large grids, and therefore also the minor of the grid that we excluded. So can we weaken that further? Can we let X be something other than a minor of a grid and still get this implication? No. If X is not a minor of any grid, then all grids are allowed in forb X, right? Forb X are those graphs that don't contain X as a minor. So all grids qualify, because we're just assuming that X is not a minor of any grid. But if all grids are still in forb X, then the tree width of those graphs in forb X is unbounded, because all the grids are in there. Okay? So this is true that forb X has bounded tree width. If and only if X is a minor of some grid. Which graphs are minors of some grid? Yeah, planar graphs. Certainly, minors of grids are planar. And the other implication is also true. If a graph is planar, then it is a minor of some grid. And here's a bullying kind of proof of that. So take your planar graph and use your magnifying glass, make it really, really big. So remember, our planar graphs always were piecewise linear. So we have some outgoing edges. And so on. That would be the planar graph. And we want to find a minor that it's a grid of. We want to find a grid that it's a minor of. And we just put a grid on top of this in the plane really, really finely. Right, well, what does fine mean? Well, we're in the grid now, so we can measure distances. And I want something like, if we look at two blue points, outside the neighborhood, the ball around a point that contains its straight line incident segments, like the distance between here and there, we want the minor to be finer than that minimum distance of any two such points. Like this one here, or that distance or so. Very, very fine minor. And now, of course, we can find a minor of the grid that is isomorphic to our graph. Here are some branch sets. And now we can join two branch sets hugging these piecewise linear edges in the plane by other piecewise linear edges between these two branch sets. And then in order to get a genuine minor, we do what we always do with these paths. We incorporate them into the branch set. So say this path here between these two, I don't know, half of it goes to this branch set, the other half goes to that branch set, whichever way. Right? So that's how to construct a minor in a hand-waving way of a grid that is isomorphic to a given planar graph. Yeah, so that's nice. So forbidding x as a minor bounds the tree width if and only if x is planar. As simple as that. And now, and that brings me to the last, yes, I have 10 minutes, 9 minutes. That brings me to a very simple application of the grid theorem, which is a strengthening of the Erdös-Pósa theorem. A very nice strengthening. Do you remember the Erdös-Pósa theorem? It says that we can find in a graph k disjoint cycles unless, if we can't find them, we can hit all the cycles with at most f of k vertices. And the point was that this function f is independent of the graphs. Right? So Erdös-Pósa said there exists a function f. So Erdös-Pósa says there's a function f such that for every graph and every k, either the k disjoint cycles in the graph G, or we can hit all cycles in G by f of k vertices, right? At most f of k vertices. Right, and here's an analog of that. So remember the notation of inflated H? So an inflated H is a graph that has disjoint connected sets of vertices such that contracting each of them gives us a copy of H. Right? It's the branch sets. If you take an H minor in some other graph G, you can find in G all these connected sets that are branch sets corresponding to this minor, and the subgraph of G, consisting just of these branch sets and the edges between them that make edges of H, this is called an IH. Right? So IH are also called models of H in G. So subgraphs of G that show that H is a minor of G. Okay, and the instead of cycles, which are IC3s, we can now consider any planar graph H, not just a C3, and we get the same property. So there is a function that in any graph G, we can either find k disjoint models of this particular H minor as subgraphs in G, or we can hit them all with at most f of k vertices. Much, much more general than Erdös-Pósa. Erdös-Pósa wasn't that easy, and it wasn't sharp. So here's a very, very neat and short proof using the grid theorem. So proof of the corollary that's up there. What do we do for k equals 1? We want either one copy of one IH, we want one IH unless we can hit all of them by f of 1 vertices, so 0 will do, right? Either we have a copy, in which case we're happy, or if we don't, then 0 vertices suffice to hit them all. And now we define f recursively. We define f of, say, k plus 1 recursively from the definition of fk as follows. We first ask, we're happy if we have k plus 1 disjoint IHs, right? We're happy if we have k plus 1 models of H in our graph G. Well, let's just choose a grid big enough that in this grid we have k plus 1 disjoint models of H. That's possible because the disjoint union of k plus 1 models of H is planar, and every planar graph is contained is a minor of some grid, right? So let's consider a grid big enough to contain these things, those that we want. Well, this grid will be present as a minor if the tree width is large enough. Let's call this W. Say WK plus 1. WK plus 1 is the tree width that forces a grid minor big enough to contain k plus 1 copies of H, models of H, disjointly. Okay. So there'll be some more things coming here, but the proof will then say, okay, let our graph be given, and either we have our disjoint copies or not. If we don't have our disjoint copies, then the tree width is less than this W, right? Because if it was at this big, the graph would have this grid minor that contained our disjoint copies. So if we're not home, then the tree width is at most W. So let's take a tree decomposition of width at most W, or let's say less than W, right? Now, ask each of these Artesian sets, is there an IH on this side, or is there an IH on this side, perhaps? And put arrows on this adhesion set accordingly. If we if the answer is neither, then this adhesion set hits all the models of H that we have. If there's none here and none there, then that's what we want, right? We have been able to hit all the copies of the models of H with W even one less vertices, namely this adhesion set. So we may assume that no adhesion set hits them all. So let's put an arrow on adhesion sets to where such a model of H lies. So these arrows could go both ways. If the arrows don't go both ways, never, we'll have a sink. And the sink will signify that there is no copy, no model of H on the wrong side. Right, that's why these arrows are towards the sink. So every model of H is hit by this bag, but that's fine because this bag has only that many vertices. Okay, so the only case that remains to consider is that there does in fact exist a two-way arrow. So now we know that on both sides there's a copy of H, a model of H, this side on that side. But that's good news, because now we can cover by induction all the models of H that are on this side by at most f of k vertices, right? Because we're not counting this here, so we don't have to cover the k plus 1 models, we only have to cover k models, and that can be done by f of k vertices. And likewise, on the other side, all the models of H in this part of the tree decomposition can also be covered by at most f of k vertices. So together, we need at most 2 f of k vertices for models of H that don't hit this central bag, or rather, that don't hit this adhesion set, and the adhesion set itself is no bigger than that. So we've hit all the copies, all the models of H in our graph by this many vertices, and that's it. So that just works. I mean, compared to the Erdös-Pósa proof itself, this is just so much simpler. But the grid theorem is not exactly that simple. So even if you don't care about the bound in the grid theorem, the proof is something like 5 pages or something, a bit like the brambles proof. Or, yeah, and it used to. If you want to look it up, go to an earlier edition of the book, and then you have the grid theorem proved in there. But with all the bounds and so on, doing that explicitly is a bit cumbersome. So that's why I took it out. Yeah, any questions? No?